Hello everyone. Today we are going to talk about Dijkstra's path algorithm. But before that, let's check out what it's actually pronounced.
Dijkstra.
Okay, so in this video, we're gonna look some real life scenarios, how the algo works, pseudocodes and time complexities, and drawbacks of this algo. So now let's see a real life scenario. There are 4 places: home, school, store, and restaurant, and there are several routes to going. Now let's think that home is our source destination. Now we want to go from home to school, store, and restaurant, but we need to go to the shortest distances every time. So if we actually just get the shortest distances, we see that from home to school it's 1 kilometer, from home to store it's 2 kilometer, from home to restaurant it's 6 kilometer. So let's just see how we can go from home to school. We can go from home to school using this path. It's easy, it's only 1 kilometer and it's the easier way. But if we think about from going to home to store, we think that this is the way. However, this is not the way. We can see it's 3 kilometers. However, if we go from home to school, then to store, we can see it's 1 plus 1, which is less than 3. So this is the optimal way, home to school to store. Again, we can go to restaurant by like going from home to school to restaurant, but it will require 11 kilometers. However, if we go from home, school, store, and then restaurant, then we can see it will only take 6 kilometers, which is the shortest distance. So there are many ways this Dijkstra algorithm can be used. Mostly it's used in GPS and networking places. So now let's see what's the goal of this algorithm. Given a weighted graph, it can be any graph like directed or undirected, G, a source vertex S, and this algorithm returns the shortest path from S to any of the other vertices. Okay, here's an example. This is a graph which is a uh, weighted graph and it's a directed graph. We can actually do this algorithm for undirected graph as well. So A is the source node here. Now let's create a table. Now we can see that A is the source. So if we go from A to A, its distance is going to be I mean 0, right? So we put it 0. Now we don't know what's gonna be the other values at first, I mean, so we put this infinity. Now we also don't know the previous except for the A, and now A's previous is nothing, so it will be null. We also put others null. It's because we don't know them now. Okay, so now what is the smallest distance here? It's A, right? Because 0 and others are all infinity. So from A we can go to B and D. So B's value will be changed to this 4 and D's value changed to 3. Oh, sorry. Now they all came from, I mean B and D came from A. So previous will be changed to A. Okay. Now, so A is done. Now, what's the smallest here? it's D. So we go to D and check where we can go. We can go to C and F. So if we go to C, the distance should be 3 plus 7, which is 10. And if we go to D to F, it's 8 plus 3, 11. So F is going to be 11 and C is going to be 10. Also the previous of these two is going to be D. Nice. So D is also done. Now what's the smallest here? It's B. Okay. So now from B, if we go to, we can go to E and C. Now here's the catch. If we go from B to C, so its distance is 4 plus 3, 7, which is lower than its present value. So we can actually replace this value with 7. So C becomes 7. Also, it now doesn't come from D, it comes from B now. Okay. So now also we also can go to B from B to E. So it becomes 6. So E becomes 6. And it also becomes B. Perfect. So B is done. So now what's the smallest here? They are done. They are not gonna be bothered anymore. So we can see E is the smallest. So let's consider E. From E, we can actually only go to 1. If we 6 and 9, then it's 15, which is not less than the current value. So we don't do anything and E is done. Now, what's the smallest? C or F? It's C. So from C, we can go to E and we can go to F. So its current value is 7. And if I add 7 plus 1, it's 8. So it is not smaller. So we don't do anything. Also, 7 plus 5 is equal to 12, which is not also smaller. So we don't do anything. So C is done for. Again, F, we actually can, now again we see which one is smaller. Actually can't go from anywhere from F, so F is also done. So there we have it. We have the lowest distances from A to A to B, A to C, A to D, A to E, and A to F, which are 0, 4, 7, 3, 6, 11. Now we'll see how we can get the paths from A to B, C, D, and E, and F. Okay, now we have this table. We can actually find the paths from A to other vertices. How we can do that? So for this one, we can see that this is only from A to A. So we can see it's null. So it's only gonna be A. A to A is gonna be A. It's obvious. So now from this, it's going to, it's B, right? So A to B. So how can we find the path from A to B? So if put the B first here, then we see what's the previous of it. So the previous of it is A. So it comes from A. And we can we know that from A we can go to nowhere. So this is the path from A to B, which is the lowest path actually. So now let's do it for C. So C first. C comes from B. Now again, where does B come from? B comes from A. So this is the shortest path. Now again, do the same thing for D. So first D. What's the previous of it? A. Okay. Again, do it for B. E. Where does E come from? E comes from B. Again, where does B come from? B come from A. This is the shortest path. Again, for F, we put it here. Where does F come from? It is D. And where does D come from? D comes from A. So there you have it. These are the shortest paths from A to its corresponding vertices. We also know the distances of all of this. It's 0, it's 4, it's 7, it's 3, it's 6, and 11. So there you have it. That's the whole Dijkstra algorithm. Now I'll move to our next part. So now we'll see the pseudocode and time complexity of it. So here's the pseudocode of it. So at first we can see that we put infinite and null in the distance and previous arrays and put 0 in the source destination. Then there's this min heap and we extract every element and perform the relaxation. So what is relaxation? This part is actually called the relaxation part. Here we actually change from infinity to other values like 3, 4, and etc. So this process is called relaxation, and this part is actually the relaxation process. Now let's find out the time complexity of it. How can we do that? So we can see that this part here actually it has O of one time, O of one time, and this one will also take O of one time, but it runs for V times. So this will total take O of V. Now we are using a min heap here, so it will require a heap function. So for building a heap, we know that it requires O of n time, which is O of V here, because we are dealing with vertices here. Now for the extract min, so we know that from extracting a value from min heap, it requires log V time. However, how many times this log V should be running? We will extract every vertices from the min heap, so this will take O of log V, V log V, because it will run for V times, so V into log V. Now this relaxation process here will not run for actually every edges but most of the edges will be covered here, so we can actually say that it will take log of V times to relax. And how many relaxation do we need? Even though we do not need to relax all of them, but we are actually checking if we need to relax them or not. So we actually basically need to check all of the edges. So this will actually go for O of E log V times. Okay, so this is our basic total time complexity. Sorry, this is our total time complexity. Now what is the dominant part here? These two are dominant parts, that's correct. Now in any kind of graph, always the edges are more than the vertices, so the main time complexity here is E log V. This is the time complexity of Dijkstra algorithm. Okay, Now, what are the drawbacks of this algorithm? Now, here you can see there are two graphs, two separate graphs. Both of them has a negative edge. So let's try to find the shortest path of this. So A um, is the source node. Now from A we can, so first of all let's give them infinity. So from A we can go to B. So and this was 0. So from A we can go to B. So this becomes 3, and from A to D it becomes 5. Perfect. Now what's A is done for? Now what's the shortest between B and D? And C, it's B. From B we cannot go to anywhere, so B is done. Again D, from D we can go to C, so 5 plus 2 is 7, so this becomes 7. Perfect. So this is also done. Now let's check. From A to B the shortest distance is 3. Is it right? 5 plus 2 is 7. 7 minus 3 is 4. So yeah, 3 is the correct answer. From A to D it's 5, A to 7, all are right. So even if there was a negative edge, it was giving us correct answer, right? Now let's do the same thing for this. From A, again we give 0, infinity, infinity, infinity. So from A to B we give this 3, again we give this 5. A is done. Now what's the shortest? B. B is done because we cannot go anywhere. From D we can go to C, so C becomes 5 plus 2 7. Our Dijkstra is done, but are they actually correct? Let's see. From A, if we go to B, it's written 3, but is it actually 3? From A to D to C to B, what's the cost? 5 plus 2 minus 10. 7 minus 3 minus 10, which is minus 3. Isn't minus 3 less than 3? Yes, it is. But what Dijkstra is giving us, it's giving us 3. So once it gave us correct answer, even though there is a negative edge, but it gives us wrong answer for another value. So when there is a negative edge in, negative weighted edge, the Dijkstra algorithm may or may not work. This is the drawback of this algorithm. Thank you. Thank you so much for listening to me. That's all from me. Thank you.